What is a transverse wave? A transverse pulse is a single disturbance in a medium. A pulse is just one disturbance. The transverseness refers to the fact that the pulse is moving along there, but the medium goes up and down. We've played with slinky springs to see what happens here. And the slinky spring goes up and down, but the energy transfers to the right. The disturbance is at right angles to the direction of motion, and that is going to be your definition on transverse. The size of the disturbance from the mean position is called the amplitude. The mean position is where it was sitting if it was still, and that is the amplitude of the wave. So C is my amplitude, and we've looked at slinky springs, looking at different amplitude, different pulse lengths, reflecting pulses from fixed and free ends, which I'll show you an animation of now, and the speed of pulses when the slinky has little stretch and greater stretch. In other words, when it's highly tense and when it's not. So there's a brilliant website. It's called FET. It's run by the University of Colorado. I highly recommend you use it often. You can go into the simulation over here, which is called Waves on a String, and watch the following things happen at your own leisure. You can play with tension and dampening and things like that, but I'm just going to show you one little thing on fixed and free end reflection. So this is a fixed end, and we're going to have a reflection. Up becomes down, down becomes up becomes down. So as it gets reflected, up becomes up when it's loose end. Down becomes down. Up is up. Up becomes down. I'm going to play it one more time just to show you exactly what I mean between the difference between a loose end reflection and a fixed end reflection. So over here we've got a fixed end, down, down, up, down, loose end, up, down, down. So those are the two different types of reflections you can experience. So free end reflection is not inverted, whilst a fixed end reflection is inverted. So it would come in on the up and go out again on the down, whilst when it's free end, if it comes in on the up, it goes back out again on the up. Transverse waves. The transverse wave has got energy that is going to go in some particular direction. Waves are a transfer of energy, and a wave is a number of consecutive pulses. But if the wave is going in one direction and the particles are going up and down in the opposite direction, we call that a transverse wave at 90 degrees. So in this case, the water wave is moving along, but out at sea, you would be bobbing up and down. So the water particles go up and down. You mustn't consider right at the coastline, because at the coastline, the water is getting shallower and the wave overtakes itself. But out in the depths of the ocean, beyond the breakers, you would be going up and down. If you were sitting in a stadium, the Mexican wave would move around the stadium, and you as a person would go up and down. Notice that these are at 90 degrees to one another. That is a transverse wave. Now, if I just take a look at this particular wave over here, if we look at the black wave first, and we see that point, now that the black wave moves to the right and becomes the red wave. And can you see the particle has simply moved upwards? And it moves further to the right, becomes the yellow wave, and the particle has simply moved upwards. So notice how the particle in the wave is moving up and down, but the wave is moving to the next position. You can watch a little bit of a video on this. What you're going to do is keep an eye on only the yellow dot, for example, or only the red dot, and see what happens to it. So you can see over there that the yellow dot is simply moving up and down, up and down, up and down. Let's watch it one more time. The wave is moving to the right, but the yellow dot just moves up and down on its line. It's also important to notice that as the wave is moving to the right, this yellow point over here was further up. As the wave moves to the right, what is going to happen? The next thing that's going to happen is it's going to go further downwards. Even though the wave looks like it's going up, the next place that's going to come in there is where this blue dot is lower down. Let's label a wave. From one peak to the next peak is called the wavelength. This is a peak, the top of a wave. Those are all peaks. This is another peak. This is a trough. And the height from the mean position up to the top or from the mean position down to the bottom is called the amplitude. So a transverse wave, the amplitude is from the mean position to a peak or from the mean position to a trough. These are called crests or peaks. These are called troughs. This is your mean position or your line of zero disturbance. And from A to B is a wavelength. A and B are said to be in phase. These 2 points are in phase. What's important is that C and D are not in phase, because at C the wave is coming down and at D the wave is going up. That's not the same point. They're not one wavelength apart. One wavelength is when I am going up and I'm going up again. So D and E are, for example, one wavelength apart. We abbreviate wavelength with a abbreviation called lambda, and it looks a little bit like that. It's a Greek letter, and we will often use this lambda going forwards. So on that particular diagram, A, B, and C were points that were in phase, and they were one length apart. AB was equal to BC, was equal to one wavelength. If you look at your notes, you'll see that. The distance between two waves in phase points is called the wavelength. Frequency is the number of wavelengths that pass in 1 second. Amplitude is the maximum displacement from the mean position. The speed of the wave is the distance that the wave moves in a certain period of time, and the period is going to be the time taken for one wave to pass. So these are all your definitions that you definitely do need to know. Let's just take a look at what happens when I change the amplitude, the wavelength, or the velocity on a particular wave. So I'm going to change the amplitude first, and you'll see that this wave gets bigger and smaller from the mean position. Small amplitude and a big amplitude. If we change the wavelength, we're either going to make this bigger or we're going to make it smaller apart. So there I'm now making a much bigger wave. You can see you've got less waves in the picture. When I make a smaller waves, I've got more waves in the picture. And if I change the velocity, that's the speed of the wave, these particles are going to bounce up and down much more quickly. So now it's faster, and you can see that it's moving much, much faster. But everything else stays the same.